let's start our study of gases talking about the kinetic molecular theory. In this lecture, I'm going to show you some of the behaviors of gases and some of the properties of gases that you need to know about in order to study them further. Have you ever heard the term kinetic before? Probably with kinetic energy. So do you remember what kinetic means? Well, if you guessed energy of motion, you were right. Kinetic energy is the kind of energy that an object has when it's moving, and particles of matter are always in motion, even if they're particles of a solid. So what we're going to do when we study gases is to think about those particles and the motion of them. If you always keep that picture in your mind, I think the behavior of the gases will be easy for you to understand. Now, with these particles of gases being in motion, what you tend to see is that if you add kinetic energy, they're going to move faster and the object will expand. Think about like how the air pressure in the tire on your car changes after you drive for a while. Similarly, if you take away kinetic energy, the molecules are going to slow down and the object will contract. Think about how a basketball that's left out on a cold winter night goes a little bit flat. It's because the motion of the particles inside the container has changed. Well, so how do you change the kinetic energy of an object? You may remember that temperature measures average kinetic energy. So by changing the temperature, we can add or remove kinetic energy from a gas sample. Now this is how a hot air balloon works. In a hot air balloon, you have those burners that heat up the air with a flame. The warm air rises, but warm air moves faster than cool air, so it also expands, and it causes the hot air balloon to rise up into the air. Now, we've been talking about the motion of particles. If the air particles are moving around, they're bound to run into each other, and this creates a really important property of gases, which is pressure. Pressure is the force per unit area of a gas on an object. And the reason that we get pressure from a gas is caused by all the collisions of the particles with the wall of the container. Now, if you have a situation where you have a vacuum, an empty space, there's no pressure there because there's no particles. So whether you're talking about a basketball or a balloon or a car tire, the air pressure that you measure in those objects comes from the collisions, the air molecules with the walls of the container. So how do you measure pressure? Well, you know the weatherman gives a report every day about atmospheric pressure. High pressure, low pressure, we have those systems that move through the area. That type of pressure is also caused by collisions of particles in the air. You measure atmospheric pressure with a barometer. And there's a picture of a really simple barometer on this slide. The way it works is that the atmosphere above a liquid like mercury collides with the surface of the mercury and collides with one another in the atmosphere. That atmosphere pushes down on the mercury and it slides the mercury and forces it up into that tube. The height of that column is how the pressure is measured. So when the weatherman talks about high pressure, the height of that mercury column is larger than if there's an area of low pressure, when there's less collisions. Also at high altitude, think about in maybe Denver, Colorado. If you're a Broncos fan, you know they play at Mile High Stadium. A higher altitude has fewer particles. People say the atmosphere is thinner. What they're talking about really is that there are just fewer particles, so you have fewer collisions and you have lower pressure. Athletes a lot of times will train in high atmospheres because it helps them when they come back down to sea level to be more in shape for their event. Now here's another type of pressure that I want you to know how to measure. Vapor pressure is something that can be measured in a lab. If you look at the slide here, we're still looking at collisions of particles. Vapor pressure, though, is when a liquid evaporates and you have those vapor molecules above the surface of a liquid. It causes it to exert pressure. The more vapor you have above the liquid, the more collisions you'll have, the higher the vapor pressure. Now this slide shows you how that's related to temperature. In the first graphic, the temperature is 212 degrees Fahrenheit and the pressure is 14.7 psi. If you lower the temperature to 180, the pressure decreases by about half, and if you lower the temperature again to 120 degrees Fahrenheit, the pressure is all the way down to 1.5 psi, or pounds per square inch. What that tells us is that at a lower temperature, those molecules have less kinetic energy, so there are not as many collisions, and the collisions are not as vigorous and as strong, so you get a lower pressure. Now we know about how pressure is measured. Let's talk about those units, because in the last slide I mentioned PSI. You see that on the tire gauge in your car. The metric unit for pressure is the Pascal, or the kilopascal. It's abbreviated kPa. But we can also measure pressure in atmospheres, or torr, or millimeters of mercury, which remember would be the height of that mercury column. Now I've given you some pressure conversions on this slide. These are actually located in your reference table, so you don't need to memorize them. But what you do want to know is that you can use them as a conversion factor to go between one pressure unit and another one. That's going to be something that you'll do a lot in this unit. So let me show you a couple of example problems. In this problem, we need to convert the pressure of 450 kilopascals to atmospheres. And we're going to also convert it to millimeters of mercury. So let's do the atmospheres first. This is going to be set up just like every other conversion factor in chemistry. We wrote down our given first, which was 450 kPa, and then we set up a conversion factor. Now I know kPa has to cancel out, so it goes on the bottom, and I know I'm looking for atmospheres, so that goes on top. Those standard pressure values that I gave you in the last slide and the ones that are in your reference table are the numbers that make up this conversion factor. So I have 1 atmosphere for every 101.3 kilopascals. Now what happens is that kilopascal cancels with that one, and when you do the math in your calculator, you're going to divide by 101.3, you end up with an answer of 4.44 atmospheres. Let's see if we can convert that same number to millimeters of mercury. I want you to recognize this pattern. We are going to set up a conversion factor again. So I wrote down the given, 450 kilopascals, and then I set up the conversion with those standard pressures. I want millimeters of mercury on top, and that standard pressure is 760, and I need kilopascals to cancel out. That standard pressure is 101.3. So that kilopascal cancels with that one on the bottom, and when you do the math, you multiply straight across, then divide by 101.3. The conversion answer is 3,376 millimeters of mercury. So bring those notes with you. Think about how the molecules are just always in motion and running into each other and bouncing off the walls of the container to make that pressure, and we'll do some more conversions in the next few days. Before we're done, I wanted to show you the assumptions of the kinetic molecular theory. Remember, kinetic molecular refers to molecules in motion. So those are the first few parts of the theory. Matter is composed of these small particles. They're spaced really far apart, and they're always moving around. When molecules run into each other, we're going to assume there's no loss of energy. Now that doesn't always happen in real life, but we're going to think about our gas as an ideal or a perfect gas. And finally, the particles don't attract or repel one another. So keep those 4 parts in mind, and as we go through the study of gases, we'll compare this ideal gas behavior to real gas behavior. Thanks. See you next time.